The universe, in all its vastness, is not a realm of pure chaos. It operates according to fundamental laws that govern everything from subatomic particles to galaxies. Thermodynamics, the study of heat and energy, is crucial in understanding the universe. From car engines to nuclear reactions in stars, thermodynamics explains energy transfer. A key concept is entropy, a measure of disorder in a system. Entropy is often described as the arrow of time, increasing in an isolated system. Over time, a pristine room becomes disordered, illustrating entropy. This tendency towards disorder is the second law of thermodynamics. Understanding entropy is crucial for comprehending phenomena from engine efficiency to the universe's evolution. Imagine a deck of cards, freshly opened and arranged in perfect order. This ordered state has low entropy. Now shuffle the deck. The cards become mixed, the order is lost, and entropy increases. Entropy measures how many ways a system's components can be arranged while maintaining the same properties. In a gas, entropy relates to the number of ways molecules can be distributed within a volume. High entropy states are more likely because there are more ways to achieve disorder than order. The second law of thermodynamics tells us that in any closed system, entropy will tend to increase over time. This is why ice melts in a warm room. The Gibbs paradox emerges when we consider what happens when two different ideal gases are allowed to mix. Imagine two containers, each filled with a different gas, separated by a partition. When the partition is removed, the gases spontaneously mix, eventually reaching a uniform state. This process is intuitive and aligns with our everyday experience. Classically, the entropy change upon mixing is calculated based on the idea that the gases are distinguishable. We assume that we can track the individual molecules of each gas. This leads to a non-zero entropy change, reflecting the increased disorder as the gases mix. However, the paradox arises when we consider two identical gases. If the gases are truly identical, their mixing shouldn't produce any observable change in the system. After all, if the molecules are indistinguishable, how can we say that any mixing has actually occurred? This leads to a contradiction. Our classical calculation predicts an entropy change, while our intuition suggests there should be none. The Gibbs paradox, then, is not really a paradox, but rather a signpost pointing towards the limitations of classical thermodynamics. The paradox arises from the assumption that even identical particles are fundamentally distinguishable. This assumption, while intuitive and often useful in macroscopic contexts, breaks down at the atomic level. The resolution to the Gibbs paradox lies in the realm of quantum mechanics, which governs the behavior of matter at the atomic and subatomic levels. One of the key insights of quantum mechanics is the concept of particle indistinguishability. Unlike classical objects, which can always be distinguished by their unique trajectories, quantum particles of the same type are truly identical and fundamentally indistinguishable. This indistinguishability has profound consequences for our understanding of entropy and the behavior of matter. When calculating the entropy of a system of identical particles, we must account for the fact that exchanging two particles does not result in a new, distinguishable state. This quantum mechanical correction to the entropy calculation eliminates the paradox, bringing our theoretical predictions in line with experimental observations. Section 5. Quantum mechanics to the rescue. Quantum mechanics provides a framework for understanding the indistinguishability of particles and its implications for entropy. The concept of wave-particle duality, central to quantum mechanics, suggests that particles do not have definite positions and momenta, but rather exist as probability waves. These waves can overlap and interfere, making it impossible to track individual particles within a system of identical particles. The Pauli exclusion principle, another cornerstone of quantum mechanics, further reinforces the idea of indistinguishability. This principle states that no two identical fermions, a class of particles that includes electrons, protons, and neutrons, can occupy the same quantum state simultaneously. This principle has profound implications for the structure of atoms, the behavior of matter, and the stability of stars. In the context of the Gibbs paradox, the indistinguishability of particles as dictated by quantum mechanics resolves the apparent contradiction. When calculating the entropy of mixing for identical gases, we must account for the fact that exchanging two particles does not lead to a new state. This quantum correction eliminates the spurious entropy of mixing that arises in the classical treatment, bringing our theoretical predictions in line with experimental observations. Section 6. The importance of distinguishability. The Gibbs paradox highlights the crucial role of distinguishability in determining the entropy of a system. When particles are distinguishable, as in the case of different gases, their mixing leads to an increase in entropy. This is because there are more possible arrangements of the particles after mixing than before. However, when particles are indistinguishable, as in the case of identical gases, their mixing does not lead to a measurable increase in entropy. This is because exchanging two indistinguishable particles does not result in a new observable state. The distinction between distinguishable and indistinguishable particles has profound implications for our understanding of the universe at both the microscopic and macroscopic levels. In statistical mechanics, the branch of physics that deals with the behavior of systems with many particles, the indistinguishability of particles is crucial for accurately predicting the thermodynamic properties of matter. Moreover, the concept of indistinguishability has played a crucial role in the development of quantum statistics, which governs the behavior of systems of identical particles. Two types of quantum statistics, Bose-Einstein statistics and Fermi-Dirac statistics, dictate the behavior of bosons and fermions, respectively, and have profound implications for our understanding of phenomena such as superfluidity, superconductivity, and the behavior of matter at extremely high densities. Section 7. Implications for our understanding of the universe. The Gibbs paradox, while seemingly esoteric, has profound implications for our understanding of the universe. It highlights the limitations of classical physics when applied to the microscopic world and underscores the importance of quantum mechanics for accurately describing the behavior of matter at the atomic and subatomic levels. The resolution of the paradox through the concept of particle indistinguishability has led to a deeper understanding of the nature of entropy and its role in the evolution of the universe. It has also spurred further research into the foundations of quantum mechanics and the relationship between the microscopic and macroscopic worlds. Moreover, the insights gained from studying the Gibbs paradox have found applications in diverse fields such as chemistry, condensed matter physics, and even information theory. The concept of entropy, refined by our understanding of particle indistinguishability, continues to play a crucial role in our efforts to unravel the mysteries of the universe, from the smallest scales to the largest structures. Section 8. Unresolved questions and ongoing research. While the Gibbs paradox has been largely resolved through the lens of quantum mechanics, it continues to spark debate and inspire new research. Some physicists argue that the paradox highlights subtle issues related to the interpretation of quantum mechanics and the nature of measurement. Others are exploring the implications of particle indistinguishability for our understanding of gravity and the evolution of the early universe. Some even speculate that a deeper understanding of indistinguishability could hold the key to unifying quantum mechanics and general relativity, the two pillars of modern physics that remain stubbornly incompatible. The Gibbs paradox serves as a reminder that our understanding of the universe is far from complete. It highlights the importance of questioning our assumptions, exploring new theoretical frameworks, and continually refining our models based on experimental observations. Section 9. Conclusion: A universe of mysteries. The Gibbs paradox, a seemingly simple thought experiment involving the mixing of gases, has led us on a journey to the heart of quantum mechanics and the very nature of matter. It has forced us to confront the limitations of classical physics and embrace the counterintuitive world of quantum phenomena. The resolution of the paradox through the concept of particle indistinguishability has not only deepened our understanding of entropy and the behavior of matter, but has also opened up new avenues of research in diverse fields. The Gibbs paradox serves as a testament to the power of human curiosity and our relentless pursuit of knowledge. As we continue to probe the mysteries of the universe, we can be certain that new paradoxes and puzzles will arise, challenging our assumptions and pushing the boundaries of our understanding. The journey of science is an ongoing one, filled with unexpected twists and turns, and it is the embrace of these challenges that drives us ever forward in our quest to comprehend the universe and our place within it.